Hello everyone, and welcome to this webinar on blade de-icing systems and related damages and the consequences that they can lead to. My name is Morten Hanberg, and I'm the Chief Blade Specialist in Wind Power Lab and one of the co-founders. Before we dive into the de-icing on blades, let me just give you a brief presentation on Wind Power Lab. Wind Power Lab is an AI-based company located in Copenhagen. We deliver repair recommendations on blade defects and asset management insights to the global wind industry. We use this using operational expertise powered by technology. And what we try to solve for our clients in terms of in relation to de-icing system is to understand how they work and what can go wrong and how we can actually fix it. But before we get to all that, let's talk about what is a de-icing system and how they in general work. But firstly, what we see in the industry is that if you have turbines operating in cold climates and you don't have a de-icing system, or you're operating in climates that get a sudden wave of in an area that gets a sudden wave of cold climate, as we see in Texas, and your turbine isn't sufficiently weathered, and in the blade's case have a functioning de-icing system, then you run into a lot of downtime. That both leads to you don't get the energy produced that you're intended, and the consumers don't receive the electricity that they need. So this is a big issue when turbines stand still unexpectedly. So a de-icing system is a carbon ply that runs along the leading edge on the both pressure side and suction side. It by adding a current to the carbon ply, the carbon then generates heat that in turn then is able to melt the ice around the leading edge, which is the most consequential for the blades being able to operate. And what we see from known installations of blades of varying sizes is that the system output is often between 25 and 60 kilowatt. And if we look at what a 60 kilowatt output for an approximately 50-meter blade is, then it would mean that you would have close to 100 meters of carbon running along the blade. Typically it has a width of 0.6 meters, which gives us an area of just about 60 square meters. What that then means is that we have an effective energy of 1 kilowatt per square meter. So that is the available energy at any point in the blade surface. What temperatures this lead to is very dependent on what the wind conditions are, the local temperatures, and so on. So we won't dive too far into that, but we know that this typically is sufficient to de-ice the blades in most situations. So when we have a functioning de-icing system, that means that the blades can then run. But we also know from the industry that sometimes these systems, they are being put out of commission, and they don't function as intended. And what we're looking into a lot more later on, a bit further down in the presentation, is what is actually the cause of this? Why do they fail? What are the defect or origins in all of this? So what we're going to talk about now is then de-icing system operating in cold climates and what you can actually do. So firstly, when you're building a wind farm and you're installing de-icing, factory QC is always a really good way of mitigating some of your issues. You can do this by checking that the de-icing system is properly applied to the blades. You can check adhesion properties, but you can still check that there are no irregularities in the surface of the blade that could lead to any problems down the line. And the most important check for a carbon-based system is the system functionality test, where you simply apply heat and then with the thermographic camera is able to determine is the heat distribution as it should be. Are there any hot spots or cold spots that you need to be aware of, and that could that would limit the functionality of the de-icing system. This is something that whenever you're building a wind farm, we strongly encourage you to go out and do this, and that you require the system functionality test as a part of your product acceptance. So what can actually happen to a de-icing blade in cold climates? What we see is that carbon is a material that is able to transfer currents. This also in turn means that it does generate some attractiveness to lighting. And all of these systems that are being applied, they have all been tested and checked that the distance of the carbon from the LPS system is sufficient that most lightning strikes will hit the LPS system. But as we also know from other talks in the industry, is that the LPS test does not necessarily correspond to the actual conditions that the blade is experiencing during operation. So given the differences in how lightning behaves, lightning patterns, and humidity on the blades, minor imperfection from a tested blade to the actual blade in production can all lead to a higher risk of lightning hitting outside of the receptor and damaging the de-icing system. We can also see that during transport, blades they do from time to time tend to get damaged during handling, and simply just by being adjacent to each other. Damages do occur. So what this means is that if you have a metal yoke or anything with any transport equipment that is getting out of the way and hitting the blade, that can cause a tremor or a gouge in the blade. And if it happens to occur over the de-icing system, that will cause a damage. And often this is detected, but the problem is that when it's detected, then it needs to get repaired, and that is not trivial, as we'll also talk about. And if it's not done properly, then you don't have a functioning de-icing system. So this is definitely something to be aware of, these issues, and that they are repaired, and that the system is tested before the blade is being installed. Lastly, we're going to talk about, talk about fatigue. And fatigue in a de-icing system is not necessarily the same as fatigue in other parts of the blade. First off, if fatigue happens between the blade and the blade surface and the de-icing system, it does not mean that you have an integrity issue. Obviously, you have a de-icing system that isn't functioning as it should, and that will malfunction, but it would not cause a structural damage right away. But in any case, if you have fatigue and you start to see delamination in local areas of the de-icing system, that would mean that you start to also see some additional strains in the carbon ply. Over time, this will then lead to clear separation and a detachment in the areas. And in the end, what you'll see is that you'll see a major cold spot but you'll also be able to detect that along the way. So any of the above damages will all cause the de-icing system to partly malfunction and to change the heat distribution that the blade is that the de-icing system is generating. And this the cold spot means that you don't have de-icing. The hot spot means that you have heating above the intended level, and that's what we're going to look at next. So we looked at before how much energy that was generated in 1 square meter. So if we take a dive into that, that means that for any that if you have a meter of if you have a local meter on a de-icing system, and that would mean that you would have an input effect of 600 watt as the carbon width is 0.6 meters. Then if you then go to the situation where you only have that you've had the delamination caused by either lightning or transport damage or fatigue, any of the above, and this is then reducing to the area where heating is transferred to 55%, that would give you an active width of 0.15 meters. What that then means is that the current that is going through the de-icing system remains the same. Nothing is changing, but the area where you have the damage has changed, and the effective area that can transfer the heat has changed quite a lot. And that means that the effect that we see in this local area is 4 kilowatts. And this and when you increase the local effects by a factor by 4, that means that you generate an immense overheating. We see an example of it here in the image to the right, where you have a very high hotspot on the blade on this part of the carbon laminate, and in other areas you have very cold laminate. This would mean that in the cold areas no heat is being transferred or very little, and in the hot areas the majority of the heating. And so what is important to understand, the de-icing system can heat the blade surface up to around 60 degrees in normal conditions. It will be less if you have high winds and cooling and all of that. But that is the limit. You never want to go above 80 degrees for a longer period of time, because then you are at risk of exceeding the blade's the epoxy's mold temperature, and if it stays there for too long, you will actually start to damage the laminate. And in the even worse case, where you have less, then and you have the de-icing system turned on, then we have seen that the surface have smoldered because of intense heat and even some small fires. And this is obviously a big problem, because it will cause some really extensive damage that can be very difficult and expensive to repair in this. So this should be avoided at all costs, obviously. So what we can actually do is that what we can help with is that when you have a de-icing system that is functioning as it should, then a repair can be made. It is by no means trivial, because you have to, because what you have to do is you have to release you have to make the fiber ends of the existing carbon ply visible or clean of epoxy, so that they can create electrical contact. Then they have to be then you have to apply a new carbon laminate, where you have to ensure that the contact between the fibers of the new laminate and the old one is sufficient to have a uniform heating transfer. You'll never get the same as before, because you have a repair where you only have partly contact, but the contact has to be good enough that you can actually operate the turbine. And again, the transition area cannot generate a hotspot that is generating more than 80 degrees of heat during max load of the system. And the heat transition zones must be in full length of the full width of the blade to avoid any local hotspots that can give you problems. And what we see over here is actually a repair that has been done, where the center of the new carbon ply is generating 35 degrees of heat, and in the transition zone we see just above 50 degrees, 56 degrees. And that means that you would have a temperature difference of about 80 degrees in this scenario here. And this is acceptable, but obviously we don't want to get it in. You want to have it as low as possible. But again, it can be done, and what it means is that you don't have to completely replace your de-icing system or replace your blade because of this, but you can actually repair it and get your de-icing system up and running. So what I would like you all to remember from this is that what can I do to avoid damages stemming from production, and that is by doing proper QC whenever you're building a new wind farm. What can I do if I detect a damage on my de-icing system? And that is by regular, and you need to detect it first, so you have to do regular inspections, and then you have to reach out to companies that are able to, like Windpoller, that is able to do proper assessment and determine what is the actual cause of damage. And what do I need to be aware of of an operation during icing condition? And that is simply that your de-icing system is functioning as intended, and you don't have cold spots in the area where you want to de-ice, and you don't have hot spots that generate critical issues. So from an owner's perspective, you should so as an owner, what you have to take away from this is to be in control of your assets as always, and understand that de-icing systems does carry a risk of getting damaged, and if you don't act on them in due time, you can have risk of limited functionality or actually damages being generated on your blades during operation. Thank you, everyone. If you have any questions related to this topic or blade questions in general, feel free to reach out to me. I look forward to hear from you. Thank you.